So this is a connected mass problem. We have an 8 kilogram load, and the load is here dangling on this piece of string. And we have a 4 kilogram block. And it says an 8 kilogram load and a 4 kilogram block are attached by a lightweight string that passes over a frictionless massless pulley. The block lies on a level frictionless surface. So what's going to happen is this load is going to fall downwards because of the pull of gravity. It's going to pull on the piece of string, which is going to pull the block across the table. Let's do a more complete diagram here. So here's our 4 kilogram block, and then here is our 8 kilogram load, and of course that's going to be 80 newtons pointing downwards, and then pulling back up here is the tension of the string, and then pulling forwards here is the tension of the string. And then we have our weight, which is 40 newtons, but we also have our normal force, which we can easily show is also going to be equal to 40 newtons upwards. This is a complicated diagram because we have a motion which goes horizontally and also vertically, and we're used to saying that downwards things are negative and things to the right are positive, and yet the motion which goes to the right and therefore is a positive motion then goes downwards, which is a negative motion. So it's easy to get confused. So what we do is we draw a diagram where we take out that bend. So again, this is our 4 kilogram mass, and this is our 8 kilogram mass, and our 80 newtons is in line with a piece of string, so the 80 goes like that. And then this is our tension, and this is our tension. There's nothing in the line of the motion. There's no force pulling backwards. This 40 and that Fn are perpendicular to the motion and cancel each other out, but they're also orthogonal to the motion. So this is my diagram. This is what I'm essentially interested in. And it says find the acceleration of the load once the system is released. Well, the acceleration of the load will be the same as the acceleration of the block, which will be the same as the acceleration of that piece of string there or that piece of string there, because it's all connected together by a piece of string. They don't move further away from each other or anything like that. So I say find acceleration using, and it's a Newton's second law, so it's going to be the sum of the forces equals ma. But the important thing to realize is I'm dealing with the system. I don't want these two tensions to be involved in this equation. This equation only deals with net external forces. So if I make my system this combined system, then I go the sum of the force of the system equals the mass of the system times the acceleration of the system. And if I make this my system, I see that the T's are internal. It's like sitting on your car seat pushing the dashboard of your car. Your car will not accelerate forwards because you're applying an internal force. Same goes for this. Those T's are not included in this equation because this is a net external forces and the T's are internal. So I look at my diagram and I say plus 80. That's the force that's on the edge here. There's nothing on this edge. Is equal to the mass, and I like to put down 4 plus 8 just so that when I check it I know what I did, times A. So A is equal to, it's going to be plus 80 over 12, which equals plus 80 over 12. 80 over 12 would be 80 divided by 12 is going to be 6.67 meters per second squared, and there's my answer for that. So when you want to do the acceleration of a connected mass system, use the entire system look at the external forces, in this case there's only the 80. Take the combined mass, in this case the 4 and the 8, and then you'll find the acceleration of any bit of the system or all of the system.